Hello everyone, this talk title is on student scan trajectories used in wafer scanners in semiconductor manufacturing. The authors are Yazan Arawashti and Mohammed Al-Janaidi, both from Memorial University in Canada, and Marcel Hertz from ASML and Eindhoven University of Technology in the Netherlands. In this presentation, we start by describing the problem at hand, where the anatomy of a generic wafer scanner is presented, followed by the role of motion trajectories, which is then highlighted. Looking at the involved processes within pick one specific process and related to the expected machine throughput. Next, we consider the making of motion trajectories accompanied with vital dimensions and terminology to consider. Then the reasons for considering higher order motion profiles are discussed, followed by 3 proposed motion profiles. Later, a multidisciplinary design optimization framework is looked at along with the associated objective function and the results obtained. We end this talk by stating some concluding remarks. Being sophisticated mechatronic systems, wafer scanners are multidisciplinary, where the involved multi-domain subsystems are interconnected. The interconnection may arise intentionally at the design level or unintentionally during operation, like vibration for instance. In such machines, various energy domains are involved and not restricted to pneumatic, electric, magnetic, thermal, and light. A holistic view is crucial to appreciate the complexity of these machines, which may weigh up to several tens of thousands of kilograms with sizes up to 100 cubic meters. According to this figure, a typical wafer scanner involves optics parts related to light and lasers, or lenses and mirrors. In addition, mechanics and mechatronic systems are heavily involved in the form of robotic handlers, anti-vibration systems, active thermal control systems, and metrology. The machine operating conditions are affected directly by the desired machine throughput, and so they will affect the theoretical design generated using computational lithography. The desired throughput is introduced to the machine in the form of motion trajectories. Being immersed in manufacturing systems, a wafer scanner must be capable of handling various internally or externally generated disturbances. Projecting the operating conditions onto their corresponding energy domains helps, for example, in quantifying the induced vibrations, thermal stresses at the reticle, optics, and the wafer substrate, also looking into the tracking errors and synchronicity besides looking into the expected die yield. Therefore, in this study, we propose a multidisciplinary design framework of the motion trajectories used specifically in wafer scanners. Dealing with a commercial production manufacturing system, the notion of time is money is highly signified. Therefore, a wafer scanner must deal with high demand rates or desired throughput associated with a certain production plan that resulted from maximizing the desired profit margin. Usually, the demand rates are given in wafers per hour. However, in this study, we converted to the die level as dies per second to relate it to the motion trajectory generation. These motion trajectories function as the heartbeats of the wafer scanner and therefore affect the energy levels needed from various energy domains. A motion trajectory plays a significant role in wafer scanners. For example, it manifests itself in the mechanical domain as structural vibration, or as tracking and synchronization errors based on its frequency contents. In the thermal domain, it shows itself as thermal loading at the reticle, the wafer, the optics through the light source illumination, and the scanning time denoted by uppercase D, and at the motion actuators through friction and repetitive motion. In the manufacturing domain, a motion profile affects the machine throughput and the die yield, and therefore the profit and the operational cost. Providing bounds on scanning time helps in reducing the thermal loading at the affected parts. This will ensure the performance of existing active heat controlling systems. A thermal load effect can be reduced if its duration is minimized and its period is maximized. At the actuators level, the thermal loading can be minimized by reducing the acceleration levels and by providing enough time for them to cool down. As stated before, a wafer scanner does exist within production lines where the received material flows through them after being processed to the next machine in the line. To identify the involved processes within a wafer scanner, it's possible to look at it in isolation, under the assumption of being ideal, where no failures nor repairs to consider. The overall machine throughput can be given as the reciprocal of the total time. The total time is defined as the summation of the times associated with the involved processes. A simplified process flow or block diagram shows the involved processes in a series connection. Other process flows are possible based on the level of granularity intended. The loading and unloading processes are associated with handling the wafer substrates, while the alignment process prepares them to be exposed. In this study, we focus on the processing phase of wafer substrates and link it directly with the motion profile generation. The total processing time to process one wafer substrate is given by uppercase T sub p, where N stands for the number of dies being exposed, and OP denotes the operation time needed to expose each die and is given in seconds. It's worth mentioning that OP can be used also to denote the processing rate given in seconds per die. To the right, a wafer substrate is shown with several intermediate traverse points that are usually obtained using path planning. These points are used to facilitate moving between rows of dies. Also, four alignment marks are shown and are used in the alignment process of the wafer substrate. Also, several line segments representing both the traverse and step and scan trajectories are shown. In this study, we focus on the step and scan trajectories whose time horizon is given by the operation time OP. Before diving into more details, it's important to mention that the scan motion occurs in the y direction while the step motion occurs in the x direction. To the right, an array of dies is shown where the dies are separated horizontally and vertically using scribe lanes needed to dice the die at the end of production cycles. In this study, we propose three types of step and scan motion trajectories as depicted in the figure to the left. Namely, they are the square, the meander, and the fillet motion profiles. Also, two phases associated with productivity are shown along with the preparation distance, the scanning distance, and the overrun distance. It is well known in the literature that better tracking and reduced vibration occurs dynamically when the reference motion profile has finite jerk values, and therefore a higher die yield is expected. Such values are associated with higher order motion profiles that can be given in the form of polynomials with continuous or switched coefficients. The following figures show a second and a third order motion profiles where the latter has finite jerk values. Matching the two profiles scanning velocities, that is denoted by uppercase V, results in the following set of equations. For simplicity, let T2 be a scalar multiple of T1. Consequently, a new set of equations will emerge. Taking K as the pivot variable, then the third order profile can be designed such that the jerk value is less than 1600 when K equals 3, as shown in the figure to the lower right. Note that this is associated with an increase of the operation time and the overrun distance as depicted in the figure to the top right, and therefore a reduced throughput is expected. So, a trade-off between die yield and throughput can be captured in the motion trajectory order. In the square profile, the motion in the xy plane is decoupled, resulting in sharp corners in the xy position. The shown timing diagram reveals the relation between the motion trajectory and the control of light beams used in the exposure process. Interestingly, it's also possible to add other items to this timing diagram to reveal the relation with other operation variables. Key operation parameters are given symbolically to the left as well. The preparation time, denoted by uppercase T sub s, should be considered when designing the settling time of the closed-loop control system. Since the motion in the xy plane is decoupled, the square profile has a higher operation time compared to the other proposed profiles, and a reduced productivity ratio is also expected. Unlike the square profile, in the Meander profile, the motion is only decoupled in the y direction during the scanning phase. This is clear from the timing diagram shown. Note that the XY position is a Meander profile and has no flat regions during the stepping phase. Both the step and scan trajectories must be jointly designed. Unlike the previous profiles, in the fillet profile, the motion is partially decoupled in the XY plane during the stepping phase. This is clear from the timing diagram shown. Note that the XY position may have a flat region during stepping. Interestingly, by adjusting a certain parameter of the fillet profile, the Meander profile will emerge as a special case. Like the Meander profile, both the step and scan trajectories must be jointly designed. Based on the previous timing diagrams, important operation variables can be defined. In this study, we focus on optimizing the operation time to generate a set of optimal solutions. These optimal solutions are used to create operation charts that facilitate selecting the operating point under given kinematical and temporal constraints. The thermal loading affects the reticle, the optics, and the wafer substrate, while the X-off and Y-off affect the cooling down time available for the actuators, assuming an actuator contributes only to the motion in one direction. Obviously, the operation time affects the actual throughput of the machine. A convex objective function is defined and minimized using the fmin con MATLAB function under the constraints shown to the right. In the shown operation charts, the selection of the operating points from the set of optimal solutions is done visually by forcing the maximum jerk value to be less than 1600. Clearly, the square profile cannot be used under the given jerk constraints and therefore got excluded. It's true that the Meander profile has a lower operation time. However, the stepping acceleration and jerk associated with the Meander profile are higher ones compared to the Fillet profile. So, it's expected that the tracking error under the Fillet profile will be lesser compared to the Meander profile. This will be looked at in a separate study. Having thermo-electromechanical models helps in specifying the feasible regions that can be inserted into the operation charts to facilitate the operating point selection. Here, a random set of feasible regions were inserted for demonstration purposes. Based on the resulting charts, it's clear that the thermal loading under the Fillet profile is less than that under the Meander profile, because the former has a lesser exposure duration and increased exposure period. Also, the cooling down time for the Y actuator is longer under the Fillet profile. Overall, the dynamical performance and die yield under the Fillet profile are expected to be the best. Before concluding this presentation, it's worth reminding that the transverse motion was not included. Also, the dynamical aspects were not investigated. This figure shows the XY position of the three profiles when processing 13 dies in the same row under an operation time of 134 milliseconds. The numeric values of the profile's parameters are summarized in the given table. In conclusion, this study covered the reference motion design problem from the wafer scanner's perspective by presenting three Steven scan profiles of third order. We also proposed an optimization framework where all the subsystems' kinematic requirements and limitations can be jointly addressed in a multidisciplinary design optimization setting. To ease the operation point selection, the set of optimal solutions can be approximated using curve fitting under the analytical expressions provided. Finally, we motivated looking into the following question: what is the best combination of orders of the step and the scan trajectories that jointly meet the desired performance and operating conditions? Thank you.